For example, so let's talk about some examples, okay? Then some examples. Take the affine line, say A1, and take the line L, say xy, satisfy the equation 3x plus 4y minus 7. So this is a so this is a line in A2, right? So you consider this map. So what is the map? So you take t goes to say t comma minus 3t plus 7 by 4. This map, so it takes the line A1 to this line L. This is a bijection and this is isomorphism, right? So what is the inverse map? So if you take 2 point x and y, you send it to x. This is a bijection. Now you check, so why it is isomorphism? So you use the theorem. These are affine varieties. So what is the, so here the coordinate ring is kt and here it is nothing but kxy by this ideal 3x plus 4y minus 7. Now this is isomorphic to kt in one variable. This is linear polynomial, right? Y you can replace by x. So this is isomorphic. So now the theorem says that if x to y is isomorphic, if and only if the corresponding coordinate rings are isomorphic, right? So then then this is but this line is, but the point is that this line is in A2 and this A1k, it is a affine line. So that is, so now you see that you don't want to differentiate these two varieties. So now you understand why you need the definition of why it should be coordinate free, why you should define it like a pre-variety. Abstractly, why one needs to define pre-variety, right? So this is a pre-variety and this is a pre-variety and this is the isomorphism of pre-variety, right? Because this locally it is isomorphic to this line L. This is isomorphic to A1. Both are pre-variety and there is isomorphism between. Yes. These correspondence also present isomorphism. Yeah. Yeah. That is easy because if you isomorphism, then that's why if you have x to y phi and if you have isomorphism, then you have a psi. Then psi composition phi is identity. So now psi composition phi will give you the phi upper star composition psi upper star, which is a map from kx to kx, and that's isomorphism. But that is the same definition of isomorphism for K algebra, right? Yes. This is true for any category. Suppose you have a category C and if you have two objects, say x, y, then you have a morphism phi. then you say phi is isomorphism, phi is iso if there exists a psi from y to x such that phi composition psi and psi composition phi both are, one is identity on y and another is one on x. Now phi, because phi composition of psi is identity, their star will go to identity, because it's a functor. So now right, okay. So now let's take another example, say C given by y square equal to x square plus x cube. So this is a curve in A2. Consider the map A1 to C. Map is t goes to t square minus 1 t into t square minus 1. So this map is certainly not isomorphism, because if it is isomorphism, it has to be a bijection. So this map is not bijection. At t equal to plus minus 1, this map goes to the same point. So first you check that this the parametrization of map. So this is a map from A1 to C. The image is in this curve. This is not a isomorphism. As plus minus 1 goes to the same point 0, 0. But if you take this, for example, this A1 to C, where C is the curve, the cusp y square equal to x cube. Then what is the, then this map, so if you take the so this t goes to t square t cube. This is a parametrization map. But this map is a bijection. But it is not an isomorphism. Because what is the coordinate ring? Here it is kt and here it is kxy by y square minus x cube. This is not a iso. Kxy modulo y square minus x cube is not isomorphic to kt. But it is a bijection. Right. Similar example, for example, if you know this, say suppose characteristic of K is P, and consider a Frobenius map. So Frobenius map, say you take a n to k to a n k, x going to x power p. This is a Frobenius map, right? So this is not an isomorphism. This sometimes it's called FP map. It's FP. This is not an isomorphism. But they are all bijection. So bijection, this theoretic bijection does not mean isomorphism. Isomorphism is little special, right? Because it involves those it has to take the regular function to regular function. So all those information which is encoded into your So the slogan is that the bijective map does not mean anything. Does not mean anything means that it does not mean isomorphism. Does not mean isomorphism. So you have plenty of, in the basic case, forget complicated variety. These are all some very basic affine varieties. In that case also it fails. So this is the point. Okay. So another difficulty is that this quasi-affine and affine, this is a full subcategory. But something here, if X is in quasi-affine, whether X lie in affine or not, that's a challenge to see. But there are some quasi-affine varieties which are always affine varieties. For example, if you take the suppose you take A n and take a polynomial f in k x1 x2 xn and consider the 0 set. So the complement of the 0 set. So this is nothing but V of f complement. That is set of all points in A n such that f does not vanish. So this is a basic open set. These are called basic open sets. This forms the base of the topology, the Zariski topology. Now this is a quasi-affine here, right? But it is affine in some in a larger affine space. Always. So for example, you take take k x1 x2 xn plus 1. And consider this polynomial xn plus 1 f minus 1. Yeah. Right. So now if you take V of this, this is isomorphic to df. So what is the map? You may consider this. You consider this map A n to A n plus 1 x1 x2 xn goes to x1 x2 xn a1 by f x1 x2 xn. So this will map from, so this is a map, so this is a rational map, so but it is defined on df. So I should not write this. So rational map means dotted map. This is not defined over whole n, where f vanishes is not defined, but it is defined on the open set df, right? But you have seen this example also, A2 minus 0. This is a quasi-affine in it. It's an open subset, right? But this is not affine, because if you call this say x, then if when you take O of x, so this will be something like OX, O of x, localization at all point, maximal ideal, or OX of P belongs to x, right? Now you show this is nothing, but now, so this means this is you prove that this is isomorphic to kxy. So if this is kxy, then you have the identity map to kxy. So the identity map should give you the inclusion map, right? But inclusion map is not an isomorphism because it's not a bijection. If it is affine, then the identity map should give you the map of isomorphism which is induced from the inclusion map. But inclusion map is not an isomorphism, right? So that's why it is not affine. Suppose it is affine, then these two categories are same, right? So OX first. So this is a little exercise you try to do, and that's.
But if it's affine, it has to be in same. The categories have to be same if both are.
That is a theorem, or that is a proposition. See, assume this, if x is affine, then the OX is same as O of A2 if they are isomorphic, right? So this is kxy to kxy. What? So this is nothing but O of A2 or A2 minus what I am saying. So this is O of x and this is O of A2. If you take identity map, right? So that means identity map I can think of is a map from kxy to k OA2 to x. So that should give which is the isomorphism. So which should give a map from your x to A2, the inclusion map, which should be isomorphism. But that is not the case. Your inclusion map is not a bijection. So that proves that A2 minus 0 is not a isomorphism. A2 minus 0 is not affine.
So, but how do you know that O of x is the intersection of O?
That's standard result.
That's only like for any subsets or only for? Is it true for only?
I think integral domain probably. For integral domain, you take the maximal ideals. Intersection. I think if you take any ring A, you can write it as intersection of AM, where M's are my maximal ideal. This is for integral domain, I think, finitely generated.
You mentioned this.
Yeah.
And how prime? Oh, this is point of.
Point of x. Hilbert, Nolster and Suss. Yeah.
Yeah.
Okay. Okay. So now from the next class onwards, I will study morphisms. See, there are various type of morphism. Most common type of morphisms are open sets and closed sets. That means open. So these are, so that's a generalization of that. It's called open immersion and closed immersion. A map from X to Y, you say it is an open immersion if the image is an open subset in Y. It is called closed immersion if the image is closed subset of Y. That is how it is defined, right? I mean, in the differential geometry or yes, injective also you require, yes. But the image should be a closed subset or image should be an open subset. Injective also, okay, of course you need. Yeah, those things will come, but derivative I have not defined so far. I am saying that these are basic maps, that open maps, open subset and closed subset. If X is a open subset of Y or X is a closed subset of Y, then here is a map from X to Y. This you want to generalize for morphisms. If you have a map from X to Y, so in some sense of injectivity, so how do you do that? So you consider suppose F, you consider X and Fx. First is that this should be isomorphism. And not only that, now whatever property you want, Fx is a closed immersion or open immersion, open subset. If Fx is a closed subset of Y, then you call it say a closed immersion. If it is an open subset in Y, then you say it is an open immersion. Right. So this is the definition make. X and Y are algebraic, I assume affine varieties. If this is a closed immersion, closed or open, if X is, so image I can talk about f of X. So if this is, if X is closed subset of Y, and if this is open subset of, if you say it's a closed immersion, and if it is a closed subset, and if you are open.
For closed immersion, X has to be closed.
Yeah, assume X and Y are affine. It's true for any quasi-affine varieties. That's fine. For example, you saw that A in the DF is a open subset, but when you take the image, it's a closed immersion. So X need not be something closed in somewhere. X is just a quasi. You can assume X and Y quasi-affine stuff. So, but you see that this AF, this definition is based on the image, how the image looks like. So the image has the property. So this is how. So what's the example? For example, if I have a morphism X to Y, and if I take a Z subset in Y, suppose this is closed, and suppose you have a morphism, then you consider F inverse of Z, then this is a closed subset. So this is so whenever you have a map of X to Y, then it gives you plenty of such examples. Or for example, if you take Z to be point, then the fibers, if you just consider, they are closed subset. So these are closed immersion.
So open set of Y is always dense, right?
Open, if your Y is affine, irreducible. So next our line of study will be study morphisms. We will define some. So I will try to see. We will define some set of morphism and study such morphism or see some examples. One implies another, so we will see such thing. Smooth map, étale map. So see first whenever you have a map, there are two things. The simplest maps are isomorphism. But if it is not isomorphism, or if it is not a open immersion or closed immersion, then there are maps like x to y. The fibers are finite. But in algebraic geometry, they are called quasi-finite maps. Finite maps corresponds to something more. They are if you call finite, if it is an integral extension. So always you have a map from ay to ax. If this map is an integral extension, if ax is an integral extension of ay, assume oy over x. So x to y always gives a map from oy to ox, we saw. Now, if it is integral extension, then you call it is finite. And you say it is quasi-finite if the fibers are finite. So finite maps are quasi-finite, but not the opposite. So these are called finite, quasi-finite. Then there are something called proper maps. So this is little bit general. Finite maps are proper maps. No, it will set closed set to closed set. Compactness is not a good definition in algebraic geometry because everything is compact. Because open sets are very big. So if you have a finite cover, an infinite cover, you will always reduce it to finite. Because the open sets are, compactness makes sense when your open sets are small. In Zariski topology, open sets are such huge objects. If you have a infinite cover, you can always find a finite cover. That's not a big deal. No, close set, but compactness is a different definition, right? Compactness, the definition is that every open cover has a finite subcover. That is the basic definition. That is the definition of compactness. But algebraic geometry, everything is compact, but everything is non-Hausdorff. It's a non-Hausdorff compact topology, Zariski topology. So the point is that what is the analog of Hausdorffness is separatedness. An analog of compactness is more special, is called properness or completeness. So we will study proper maps. There is something called local homeomorphism. Like if you take the map z going to z power n, this is from punctured disk c minus 0 to c minus 0. This is a local homeomorphism, right? Every disk locally there is it's a covering map. These maps are called local homeomorphism. These are same, the corresponding is called étale maps. Étale maps are local homeomorphism. Then there are maps like f, x to y smooth maps, which are more general than smooth variety. So they are called smooth maps.
So these are like finite maps are proper.
Yeah, finite maps are proper, but this is not true. These are more general maps. We'll see. I am not putting any, but these are properties of maps. See, by studying this, if you have some property of map, then you can say about the fiber. So that's how you understand variety. Suppose you want to understand this x. So what you do, you construct a y to z such that phi bar is x. And if you know, so if you construct this map, if you say something about this map, if you know how the map behaves, then you can talk about how the phi bar behaves. So that's how you prove result, right? So we will, in next few classes, we will study morphisms of algebraic varieties. And now, so we are so far doing with affine or quasi-affine. But then we will, at some point, we will go to the projective world or quasi-projective world. So there also it is locally looks like a affine map. So then you study that. You can, all those things, definition can be made for projective world. Projective world.
We don't need like the sheaf theory that much.
Right now, no. But at some point we will need. But this sheaf theory we need to define abstractly variety. It's locally like a affine space. But to define locally affine space, how do you define? The global object is the sheaf, a pre-variety. So everything you can define it for the pre-variety level. All these maps you can define pre-variety level. It's a map of pre-variety. Locally, it looks like this. You could say it's a finite map. If x to y is a map of pre-variety, and you have a map morphism. Morphism in pre-variety makes sense. Then you say that it has this property. If locally, they have property. Locally, after all, it's a map from affine to affine, another affine map, right? If it's a map, so what does it mean? Pre-variety means there is something A here, or spec or some affine variety. So it's a map from A to Y. Yeah. Then you can further restrict to take the image, and you can further restrict so that it's a map from A to B. They are called affine maps. The map is called affine if this is the situation. If you have an open subset, affine open subset, the inverse image is also affine. So it's a map of affine. So it's just seems. So these are called affine morphism. In affine morphism case, everything you can reduce it to the local model. So first one should understand the affine case how this map behaves. Then only you can do it for the further generalization, further study. Yeah. So I will stop here.